All right, good morning, everybody. We finished up chapter 4, which was our apportionment chapter, and now we're going to start our first lesson in what we call um, graph theory. All right, and this is Unit 5. All right, so real quick, starting out, we call this management science problems. Um, And ultimately, what we're going to do with management science problems is we're going to talk about um, these are problems in which the ultimate goal is to find efficient ways to organize and carry out complex tasks. All right, so we are going to find efficient ways to organize and carry out large number of complex tasks that do not often appear possible to make um, optimal decisions. Okay, so we're going to find efficient ways to organize and carry out a large number of complex tasks that do not often appear possible to make optimal decisions. It's kind of the whole idea of graph theory. And we're going to talk a lot about in this one um, what routing problems. What is a routing problem? And a routing problem is finding ways to route the delivery of goods and services to an assortment of destinations. All right. Finding ways to route the delivery of goods and services to an assortment of destinations. All right. And so there's two important basic questions that we have. The existence, is an actual route even possible? Okay. Is there a possible route? And if so, if there are multiple possible routes, which is the most optimal route? The best, the fastest, the cheapest. You got to think if we're delivering goods and services, like, let's say a tractor trailer, then that costs gas. So we're probably going to want to find the route that's the shortest, because the shorter you drive, the less gas you're going to use, which means it's going to be cheaper. But then on the other hand, sometimes the shorter distance, maybe you have to go through small towns and things like that where you have to drive a lot slower. So, optimal route might be going somewhere, taking, like, let's say, an interstate where you can actually get there faster. And so you got to kind of decide, in whatever your instance is, let's say this is your company, this is your trucking company, or you're on the receiving end, you're trying to get these goods and services from this trucking company, then you would have to take time and figure out what would be the best case. Do you need it there faster? So you need time cut down. So maybe you'll have to spend more money on gas, or maybe you're trying to be more cost effective and save money on gas. Then maybe time is not an option for you, but you want the shortest route. So those are all things that you would have to take into consideration. So special case of routing problems, exhaustive requirement. Route must go everywhere, all destinations and all paths. So sometimes you might have to go everywhere, and we'll talk about that. A route is called an exhaustive route. Okay, so if we have to hit every landmark and drive on every street, then that would be an example of an exhausted route. Okay, and that was pretty much the kind of introduction. You'll hear more about it, but we call this 5-1. The reason they call it, this is what we call an Euler circuit. I know it starts with an E, but it's actually pronounced Euler. So we're going to talk a lot about Euler circuits and paths and things like that. All right, so moving on then to 5.2. Here's kind of the meat of, we're going to start doing some introductory things here. And so the first thing we're going to talk about is a graph. A graph is a picture consisting of dots and lines, could be curves. This type of graph represents an area of mathematics called graph theory. and is different than graphing of functions on a coordinate plane. So this isn't like graphing a parabola or anything like that, okay? Basically, we're mapping out, you know, kind of almost like a real life scenario. Let me kind of show you here. So like here, you know, going back to what we were just talking about, like here's my map where like the post office and the park, and here's the school. And so we would maybe represent these destinations as dots, and then the roads would be my edges kind of thing when it comes to my graph. And then we would do something like this. So these could maybe be the destinations, and then these would be examples of roads to get there. So, you know, it's like a map, but it's kind of like a kind of a pared down map is what it kind of basically a graph is sort of going to represent. Now this stuff can represent different things. That was just kind of one example. All right, so the formal definition of a graph: a structure that defines pairwise relationships, edges, with a set of objects, vertices, x related to y, if and only if xy is an edge. Okay, so let's first talk about all the vocabulary. That's going to be kind of the most important part here, is our vocabulary. So the first part, your vertices. They are the dots or the points on the graph. So in my picture here, I would say maybe like A, B, C, D, and E are my vertices. Okay? And then your edges, if I talk about edges, are the lines that connect those vertices. So like AB would be an edge. AE would be an edge, so on and so forth. AD, ED, ED, okay? All right, questions there. Now, we have, let's see. So we talked about vertices, we've got edges. All right, so what if we have a loop? What do you think a loop might be? And you can kind of see it pretty clearly on here. A loop is an edge. It's an edge that kind of maps back out onto itself. So like this would be an example of a loop. This would not necessarily be a loop, even though it's kind of like, you know, circular sort of. This wouldn't be in a loop because it's going from one destination to another. This would be a loop because B, you went around and you ended up back at B. Okay. Now you might say, well, like, you know, what's the point of that? Well, I mean, once again, kind of go back to your, kind of go back to our map example. You know, let's say we went here at the post office and we went down this road and we came back this way. We still ended up at the post office. So that would be an example of like a loop. On here, sometimes you might be like, well, what's the point? Why did I even do that? But maybe we needed to, once again, we talked about sometimes if it's an exhaustive route, we might need to make sure that we drive on everything. All right, so there's an example of a loop. All right, now the next one would be multiple edges. Okay. So loop, if we want to maybe notationally, we might say like BB. So we started at B and we ended at B. All right. Now, example of multiple edges would be something where it is possible for two edges to connect the same pairs of vertices, as in this case with ED, which would be what we call a double edge or multiple edge. So there's two paths that got to ED. So ED would be a multiple edge. Okay, I'll put a line there. ED would be a multiple edge because you could go this way or you could go this way. And once again, some of you might say, well, why would something like that be? But like I said, go back to your map for a second. Go back to your map for a second. What if we're going from the post office to the school? Couldn't I go this way down this street? But I could also go this way down this street. Does that make sense? So there's more than one way to get to the same destination. And so that would be an example of a multiple edge. All right. And then we have here what we'd call notationally, our last thing, an isolated vertex. Now, what do you think that would be? Okay. My isolated vertex, in this case, would be C. All right. C would be my isolated vertex. Even though it's a dot, there's really nothing connecting anything to it. So it's all kind of by itself out there. In terms of a map, you could say maybe it's like a little island. There's just nothing around. I mean, there's just no way for me to get to it. Okay? It's its own little island. Now, we kind of talked about this already a little bit up here at the top, but we have what they call set notation. So now, if it's empty set, you have like a little bracket there, and there's just nothing in it. It's empty. Okay? So, for instance, with an isolated vertex like C over here, in terms of vertex, I would have my vertex. So once again, in set notation, they would do something like vertexes are. We kind of already talked about it. It was A, B, C, D, E. Okay. But let me show you how empty set would work. If I said I wanted you to do the edge set of things that touch C, since nothing touches C, we would just do what we call the empty set. So kind of like the two little brackets. And I know those are awful squigglies. But now here, if they want to know the edge set, so what are my edges, they literally want you to list all of them. So we have edge A, B. All right. Now, some of you say, well, Ms. Ryan, I called it BA. That's fine. But the thing is, you do not have to list it twice. AB and BA, in this regard, are the same thing. Now, if there was a multiple edge, then you would list those twice to represent there are two different ways to do that. Okay? But if it's just one, you can either call it AB or BA. You do not have to do both. Okay. So what else do we have? And sometimes, once again, I think we've done this before, just to stay consistent. Now, you could mark them in your picture. We've already done that one. All right. Let's do all the ones from A. So you would have AD would work. And we can go ahead and maybe mark that one. You have AE would work. So you can go ahead and mark that one. Anything else from A? No. Let's go to B. Anything from B? Well, outside of BA, which we already have, we could represent the whole BB. There's my edge right there. All right. Anything from C? No. Anything from D? Yes. Now, you already have D, so you could say DA, but we already have that with AD. But what's a new one? We have DE, and we have a different DE. So in this case, I do need to write, because that was the first DE, and that would be the second DE. All right? And so there would be my edges. Okay? You're literally listing them all. You just don't have to do any repeaters. Okay. Questions there? All right. So let's look at one quick practice problem. All right. So like on this one, what are my vertices? Here's my picture. What are my vertices? They're going to be, my vertex set is going to be A, B, C, D, and E. Those are A, B, C, D, and E. Very good. My edge sets. So once again, maybe start. So edge sets would be, I've got AE. I've got AB. Go from B, I got BE. I got BD. BD, and I got BC. All right. Then go from C. The only thing new would be CE, because CB is already taken care of. Go from D. I can do my loop DD, and then I have DE. Very good. Those are all my edges. Do I have a loop? Yes. DD. Do I have multiple edges? Not really, I don't think. and then isolated vertex, none. So there's my example.